Okay, perfect. Right. Let me, I don't worry, right? I recorded some of it. Well, in fact, the last two sessions I recorded fully. But the first two sessions, I think I completely forgot about it. But I'll run you through the stuff that I missed out in those videos. So I'll post it on the channel, and then you can go back and watch it, right? So you didn't miss out anything. So yeah. So let's get back to this, right? So we're saying that, where is that the calculation thing, right? So we're saying that any value that is less than -7, not equal to -7, less than -7. If I take it and I input it into here, I'm will output a negative value. See, less than 0 means negative, right? And so we've done the minus 7.1 and we saw, okay, minus 7.1 is more negative than -7. We can think of it like that. It's less than -7, and so we should output a negative value. And I've illustrated, I used a fractional value just to show, even if you're just slightly to the left of -7, slightly more negative than -7, then you will get that answer. Now what I want to do is I want to prove it to you. I'm going to go slightly above -7. So I'm going to make it minus 6.999, which is slightly more positive than -7. Right? Slightly more positive. 0.999. Right? So if you look at it here, see minus 7.1 is here. See where minus 6.99 will be? Right here. Just to the right of -7. Because at -7, it will be something. Slightly to the left, it's negative. Slightly to the right, it's positive. You're going to see it here. And if I do that, can you see we output a positive answer? And so this is why it has to strictly be less than -7. Strictly less than -7. Because if it is -7, then it is should be 0, right? Yeah. So if it's -7, let me do it like this here. Let me zoom in here. I do it like this here, and I make this here -7. At -7, what our output will be? 0. Slightly less than it, it'll be negative. Slightly greater than it, it'll output positive. Very powerful stuff. If you can understand this here, let me say this. If you can understand this, then you'll understand graph and interpretation type questions. Because this is a function. I want to find out when is this function here negative. For what values of x must I input into this function such that I output y values that are positive? See, this here is the same as this here. Right? That's why I'm looking at this function, not that. That's complicated for me to see. I just want to see this. And so if I do a quick sketch of this, the function will look like this here. This here will be -7, the x-intercept, and this here will be +21, the y-intercept. And so when I go just slightly to the left of -7, see what happens to the y values. All negative y values, outputs all negative y values. At -7, the y value is 0. Slightly to the right of -7, it's above the x-axis. Can you see that? All positive y values. Can you see that? Inequalities, functions, everything is the same. There's nothing different. Okay, guys. So yeah, so that's what we're talking about there. Okay, perfect. It's back in. Right. Yes. So yeah, that's what we need to remember. Right? When we're working with inequalities is the same as a graph and interpretation type question. Right? So yeah. Okay, so let me just run you through this, right? So we're working with this question here, okay? And in this question, we're trying to solve for the x here using an inequality. And I explained this to you before, and I know you understand it. But this part here, when we're saying this less than 0, this here is a function. This is a linear function. And so we take this and we simplify it, we get this here. And if we simplify it further, we get this here. So we want to find out where is the 3x plus 21 function, which is a linear function, where is it negative? And so what I'm saying is, what x values must I input into this function such that I can output y values that are less than 0? And so if we're saying it, looking at it from this perspective, 3x plus 21 is equal to y. At this point here, I'm saying, for what x value will y be less than 0? If I sketch this function, it looks like this here. This one here will be 21, and this one here will be the x-intercept, which is -7 and 0, right? How do I know that? Because when I solve for this here, I got -7. And so what we're saying is, If I input a value, any value less than -7 into this here and here, and here, I am certain that I will get a negative value. But if I input a value that is slightly bigger than -7, then I'll get a positive value, right? So yeah, and then I proved it to them. I proved it here. So I inputted a value that is slightly bigger than -7. -6,999 is slightly bigger than -7. I inputted it into 2x, and I inputted that value in here. And can you see? We output a positive. But that's not what I want. That's not a solution to what I want. I want it to be negative. And so if I input a value that is just slightly more negative than 7, see, 7,1, slightly more negative than 7. Do the same thing here. I know it's a bit difficult to think on the negative side, but get used to it. Can you see that? Just gives me a negative. So if you picture what I did, see, if I zoom in here, -7 is here, right? -7,1 is just slightly to the left of -7, so it is more negative. And -6,9999 is slightly to the right. So this is why we're saying it has to be strictly less than -7. Strictly less. Because if it's strictly less than -7, you output negative values. If it is -7, then it is 0, the x-intercept. And if it's slightly greater than -7, then it's positive. What's positive, what's 0, and what's negative? The y values. And if you look at it in terms of functions, at this point here, y is 0. Slightly below is y is negative because it's below the x-axis, and slightly to the right, it outputs y values that are positive, that lies above the x-axis. Right. The reason I went into so much of depth, because this is coming out, graph and interpretation. This is how you need to start thinking, graph and interpretation. And now you can literally see how everything links. Everything, from equations to expressions to even inequalities. Inequalities form part of functions. This is why I told you, if you can understand expressions, equations, and inequalities, you understand functions. And if you understand functions, then you understand these three. Very powerful stuff. Very, very powerful stuff. So, yeah. And then, yeah, then I also went on by saying that when you're talking about interval notation, we're making use of brackets. And when we talk about set builder notation, we're making use of the inequality signs, right? The general idea with this representation of sets, we basically just want to state the max, the minimum, and any restrictions that's in between the max and minimum. That's basically what we're doing. And so if I do this here with this, if I express it using interval notation, I'll say that x is the element of the smallest number is -infinity. You already know that we don't include -infinity. And the maximum is any number, or the maximum will be a number that is just slightly before -7. So that's why we don't include it. Right? So we don't include both those extremes. And there's no restriction in between, because if you think of it from the line function, that function can go on to infinity. There's no restrictions to it. Right. So yeah, so that's basically algebra, right? So let's move on to. Okay, we can do this one here too. Right, let's say that we have 20, 21. Let's say that you have 20, 21 over 1 minus 20, 20 squared. And when you're trying to solve for something like this here now, you just got to think outside the box, right? But if you look at it, I need to try to simplify this. It seems like we can't simplify it. But what are some of the simplification tools that we used? We talked about factorization so far. Factorization. So we're going to use factorization. And it makes sense to do so because I can see a plus and a minus sign here. And so what I can say is I can say that the top will be 1 plus 20, 20. And I can see a difference of 2 squares at the bottom. 1 minus 20, 20, 1 plus 20, 20. 1 is the most powerful number in maths because it's very deceptive, because 1 is both a perfect square and a perfect cube. And so sometimes you'll have this here and you'll think you can't simplify. Sometimes you'll have this here. 2, see, perfect square, perfect cube. Right? This is why it's so powerful. Then if I cancel that and cancel that, I'm left with 1 over 1 minus 20, 20. Right? We're just using tools. Same idea, rinse and repeat. Yeah. Yeah. This is why understanding, those identities that we talk about all of the time. This one here, A plus B whole squared. Under products, I spoke about the identity. When you're squaring a binomial, it's A squared, right? Plus 2AB plus B squared. This is why. Remember, we had this whole disagreement. Like, I prefer the way my teacher's doing it, separating the binomials. I don't want to use SMS. This is why it's important, right? Because if you look at this here, they say determine the value of 3p plus q all squared if 9p squared plus q squared is equal to 12 and pq is equal to minus 3. How does this link to that? If you understand SMS, you'll see it faster, and you'll see it. So what we do here now is, if I do squaring of a binomial, this will become 9p squared plus 2pq plus q squared. Can you see it? And so 9p squared plus q squared is the same as what? 12. And pq is the same as what? Minus 3. And so if I rearrange it, right, like this here, we didn't change the question, we only re-expressed it. And so this part here is the same as 12 plus 2 into PQ is the same as minus 3. And if we solve, we get 6. Can you see that? But now if you want to go and... But basically the idea is you need to remember SMS. You have to remember it. This is going to come back in trigonometric identities and it's going to bite you. So you better focus on this and get this SMS thing down. Square the first term. 2 times the first term times the second term. Right? So yeah. So that's how we do this. Because you see, when I looked at this question, I was like, okay, what links this to this? What links it? How did 3p become 9p squared? How did q become q squared? Where is the pq here? Oh, when you do the SMS, you can see there's a pq here. And that's just a constant, so I can just multiply it in and I can solve. Right? This is what we're doing. We're trying to find pieces to the puzzle and we want to know how they fit. Right? Raquel, you can see here too, right? So yeah, px plus qx equals to a. Solve for x. Can you see that? What I talked about in literal equations. When you have the variable in two different terms, that can be simplified, then we have to make use of factorization. I'm sure you can see it now. Yeah, I proved it to you. This was in a paper. And then it's x is equal to a over p plus q. It's in there. Right? So yeah. When you get this type of inequality, right? We call it, we get a conjunction inequality and a disjunction inequality. Right? I talk about that in depth in the videos. So there's it here. Right? All you got to do is, when you subtract, how do you get rid of the 8 here? You add by 8. But now you're going to add by 8 on both sides of the inequality. Okay? Again. Minus 8, y-intercept. There's it here. Positive gradient, it's going to do this. And so when you solve for m, what that m value is, I want to find out an m value that I must input in here, such that I output a y value that is greater than or equal to minus 11. So minus 11 should be somewhere here if I extend it here. So I want to input m values that will be greater than or equal to minus 11, which is somewhere here, but less than minus 4, which is somewhere here. And so if I come up here, I'm going to get this x value here, and I'm going to get this x value here. So it must be at this x value, and anything greater will give me values that will be greater than or equal to minus 11. But at this x value here, I have to exclude it, because at that x value here, what we output? 4. So now we're talking about two extremes. I'm in between these two extremes here. In between these two extremes. Can you see that? Right. So yeah. Okay. And if I solve for that, it'll be 3m, add by 8 on both sides. 7, so it'll be minus 3, right? And this, if I add it by 8, it'll be 12. And then m will be greater than or equal to minus 1. And this will be less than 4, isn't it? And so this x value here is equal to -1, and this x value here is equal to 4. Right? So yeah, and if I take this here and I plot it again on Desmos, you'll see 3m or 3x, 3m, same thing, same difference. 3m minus 8, right? And if I zoom in here, yes, c minus 1. At -1, we output a y value that is -11. At -1, wait, there's it here, at -1. So I want to include it, isn't it? I want to include -1 because at -1, I want to find out what m solutions will give me a value that is equal to -11, but also greater. So at -1, it has to be the case, right? Because at -1, we have the case where the function is equal to -11. So all of these values here will work up until 4. Because see, at 4, the y value that we output is 4. If I go slightly to the left, I output a y value that is bigger than 4. See, 4,07 is, 4,21 is bigger than 4. So if I input 4,07 and an x value that is slightly bigger than 4, I output a y value that is slightly bigger than 4. I hope you guys are understanding this. Right? If I output an x value, see, at 4, it's a solution. It's 4. But we don't want it to be 4, and we don't want it to be anything bigger than 4. It has to be less than 4. So if you put a value that is less than 4, like 3,98, you output a value that is less than 4. This is what this inequality is trying to tell us now. What m value must I input here? What x value must I input into this function such that I output a y value that is equal to -11 or greater, right? And less than 4. So I want it to be equal to -11. That's what that bar is. But it must also be greater, and it must be less than 4. And it must be less than 4. And that range of values, if I want to visualize it on a number line, will be -1 to 4. I'll have a closed circle here. I'll have an open circle here. Right. But you'll see what's going to happen. These circles here, this closed circle means we have to include that -1. If I include all of the other values, like 0, minus 0,5, 0,5, whatever, and you put dots on all of them, eventually it takes on a line. Because all of these infinitely many values that lie in between are solutions to this, right? And so this is why if you put a dot on all of the values, all of the m values that satisfy this inequality, right, then it becomes a line. It becomes a line. Okay, right? Because I can take it a step further. You really want me to push your thinking, I can take it a step further. I can come in and say m must be an element of the integer set. If m must be an element of the integer set, then the integers between -1 and 4 is what? 0, 1, 2, and 3. So only at these discrete points could we include. We can only include these discrete values. We can't say in between, because they're saying that the value of m that you can input into this linear function has to be an integer. It cannot be a real number. If it was a real number, then you join it, you put a line. But if they don't state it, then we just say, okay, no, we're assuming that they want us to put a real number. Oh, there's it here. Beautiful, there's it here. Hence, write down the number of integers that satisfy the inequality. How many integers satisfied? 1, 2, 3, 4, 5. Not the 4. The 4 cannot satisfy it because at 4, it is equal to 4. We want it to be less than 4, not equal to 4. Right? And if it becomes slightly less than 4, it's 3,999. But 3,999 is not an integer. So the number of integers that will satisfy this will be 1, 2, 3, 4, 5. 5. Right? If they tell you to represent it on a number line, this is how you would represent it. Can you see how they're pushing your thinking? But where all these ideas came from? All these ideas came from where? Functions. Remember we talked about discrete and continuous functions. Same idea. Right? When we get to statistics in term 3, we're going to talk about discrete and continuous numbers and so on. Right. Right, everyone following? You can raise your hand if must I re-explain? Can type it in the chat here. Sumesh understands. Sky understands. Dylan understands. Lamia, getting it? Yes? Right, perfect. Right, so that's that, right? So I hope you guys can see it. That you literally we're just playing with numbers here, right? So when you're doing these things, please don't go study these questions. Use your just look at the theory, right? Look at the theory, right? But when I looked at this question, like that's why when you complete a question, if you solve this here mathematically, you'll get it right, but you don't understand what you're doing. And so when I come down here to the point, I'm saying, okay, so if I input an m value that's in between -1 and 4, including -1, I'm certain that it'll output a y value that is greater than or equal to -11 and 4. When I put it on the graphing calculator, then I use to check. I'm saying, okay, yeah, in fact, it does work like that. And then this is how they create level 4 questions, like higher order questions, because you don't understand, like, where does this even relate to functions, right? This is why you need to see these things, okay? Because if you show it in terms of functions, that you'll understand what I'm saying. And then if you go more in depth, like discrete and continuous, you'll understand it even deeper, right? Because they could have easily said, okay, represent the number of integers that would satisfy this inequality on a number line. Then you have to put closed dots on all of the integers, but on 4, you have to put a open dot. But if they say, write down the number of or they say, write down or draw this on a number line, the solutions that satisfy this inequality, they didn't say whether it has to be an integer, natural number, or whole number. Then we just assume that they're talking about a real number. You have to join all of this together. Because if you did that for the infinitely many real numbers that make this, that come in between, they still satisfy this inequality. Eventually, it does not become a point. It will take on a line. This line here is in fact made up of many points. That's why it becomes a line. Okay, so yeah, that's like some of the higher order questions that you could get. But I honestly don't. Um, yeah. Yeah, see, this is a nice question. It's a very nice question. Remember, I brought up the whole thing about restrictions, guys. Restrictions, I talked about the fraction, I talked about the square root, and I talked about logs. There's yeah. You see, when I look at this here, for which value of values of x is m? Undefined. When is a number undefined? When you divide by 0. So the denominator cannot be equal to 0. The denominator cannot be equal to 0. There we're talking about a fraction and the square root. Can you see how they're testing you on your restriction questions in one? They're giving you a fraction and the square root. I know that the square root, the radicand, everything that's under the square root cannot be negative because the square root of a negative number is non-real. Division by 0 is undefined. Square root of a negative number, non-real. Okay. And yeah, so if I do that, when is this undefined? It'll be when x minus 1 is equal to 0. When x minus 1, this whole denominator is equal to 0, then it's undefined. But then I can go a step further and I can pinpoint what that value is. So at 1, this function does not exist. At 1, right? And can you see what I just said now? I said function. I didn't say expression, I said function. Go plot the square root of x over x minus 1 on this Desmos calculator. When you come to x equal to 1, you'll see it'll tell you it's an error. It'll tell you it's an error. This is why I keep saying it. Functions is the most important topic in maths. Divided by x minus 1. Yes? There's this function. I guarantee you don't even know what this function is. But you're going to sketch it when you get to university. Right? See. Can you see what's happening? This is like more like an hyperbola. Can you see it? Can you see what's happening? It's going so far up, but it never becomes 1. It never becomes 1. Right? Because you have an asymptote. In this case, you have an asymptote. That's why. Can you see here? I'm getting so close to it. I'm just a fraction above 1, but I'm never getting to 1. I have a far. See where my cursor is? There's my cursor here, this white thing. It's not taking me higher. It's not taking me higher. Right? So that's why we say at x equals 1, it's undefined, or it can never be equal to 1, because that's an asymptote. Higher order stuff coming from where? Functions. When will it be non-real? Square root of a negative number. So what more specifically, the radicand. So Lamia, the radicand is everything under the square root. This is called the radicand. Right? And so when will it be non-real? When x is less than 0. But I can go a step further. I could have changed this question. I could have said, okay, square root of x minus 2 over x minus 1. And so now the answer won't be x less than 0. It'll be everything under the square root If it's less than 0, then it will be non-real. But now I can go a step further and pinpoint what those values are if I solve for x. So for any value less than 2, it will be non-real. But obviously they made it simple for you guys, and they just put x there. Yes, guys. Right, I can go even a step further, but that'll be grade 11 stuff. And for what values of x will it be real? Right, for what values of x will it be real? Right, watch how brilliant this is. Watch how brilliant this is. If you understand your real number systems properly, it's made up of real and non-real, R and R prime, R and R prime. And then we had undefined, right? Undefined stood on its own. Right. Listen to this. I can input any value into this here. Any value will be x element of real. I can input any value, x element of real. No, wait. Wait. There's it here. Wait, what? Sorry, my bad. Wait. We're saying that for x values less than, x values less than 0 is what? Non-real. X values less than 0 is non-real. Remember, what did I say? I said real and non-real are what? Inverses of each other, right? And so if any x value is negative, if it is negative, then we have what? Non-real numbers. So therefore, if we want real numbers, it has to be positive, right? They are inverses. They are inverses of each other. This is like black, that's white. Yes, no. It's binary. True, false. Yes, no. Yes. And so it'll be for x values greater than 0. But then you must ask yourself, can x be equal to 0? Can x be equal to 0? Yes, it can. It can be equal to 0 because if I put 0 there and 0 there, I do get an output. So that works. Yes, you know, guys, just one more thing I mentioned in the inequality video. Whenever you're working with inequalities, always ask yourself, can I put that bar there? You must always ask yourself that. I could see if I just did this here, if I use the logic that I just did, and I said, okay, for real, it's just the opposite of non-real. So if this is negative, that must be positive. But then I didn't test whether it can be equal to 0. I get this answer wrong, and it's only 1 mark. So always ask yourself, see here, I can't put equal to 0 because at 0 it does exist. It does exist at 0, but for anything less than 0, it does not exist. So here I can put equal to 0, but now if you've been paying attention, if I put in 0, x greater than or equal to 0, I'm going to pass 1, isn't it? I'm going to pass 1. Think about the number line. I am going to pass 1. But we know at 1 it's undefined, so therefore we have to say x cannot be equal to 1. Right? Go back to functions. Go back to functions. Here's it here. At 0, it exists. Any value greater than 0, it does exist, provided that it's not equal to 1. Can you see how all these x values are getting closer and closer? 0.998 is getting so close to 1, but it never becomes 1. Why? Because we got an asymptote at that point. We have an asymptote at that point. Why is it not? Yeah, but we got an asymptote at that point, which we've already discovered, because the denominator cannot be equal to 0. That's why we say x cannot be equal to 1. Right, logic. Yes, no. Black, white, they're inverse of each other. Test. Whenever you got an inequality, check. Can I include that solution or do I not include it? In this case, we have to include it. And then you have to realize, okay, now if I continue going on to the right, 1's going to be there, but I already discovered that 1 is undefined. And but you know what? It's coming back to what I just said. When you're writing solutions or sets, you state the maximum, you state the minimum, state any restrictions in between. What are restrictions? Fractions and square roots. And logs. I'll add this here just for the sake of it. Logs. And so the minimum value could be 0. The maximum value from this is what? Positive infinity. Between 0 and positive infinity, are there any restrictions? Yes, there are. I'm coming to 1. Why? Because the fraction, the denominator is 0. Guys, I hope you'll understand what I'm saying. Right? This is the power of it. State the maximum, state the minimum. Are there any restrictions in between? The way you'll figure that out is if you have fractions or square roots, right? For the fractions part, we did realize that it's undefined, so we have to state that restrictions. For the square roots part, Remember, we just said that they are inverses of each other. So we don't even have to bother about it, right? Because it can't even be that. It'll be everything opposite to it, right? So that's why we'll take that out and we'll say it'll just be real values. But this is coming all from functions, guys, all from functions. Okay, yeah. See, year two, if I look at this here, see, power of one. One is so deceptive. If I look at this here, this is a perfect square minus a perfect square. We're doing factorization, so we'll make use of the difference of two squares. So first check if there's an HCF, then check the number of terms and go from there. Here, you can see if you distribute the bracket, you'll see that there's 4 terms in this expression, so you're going to make use of grouping. Right, but if you look at this here, you can see that this here and this here, these binomials or the binomial factors, they look the same, but we just need to make like a difference to it. We need to change it slightly. And so if we do that, let's change the first one. Because one term has a negative on it, we can use the change of sign rule. So this will be minus a squared over 9 into b minus 3 plus b squared over 16 into b minus 3. Now that I have a common binomial factor, I can extract it, and I'll have the following. Right, so now we did factorization, isn't it? But what's the last thing? Distribute and check. If I distribute, I will get that. So we're done. What do we need to check? We need to check that every factor is factorized fully. When you do that, and if you did it correctly, you'll realize that I can use dots again here. And so this will become b minus 3 into b over 4 minus a over 3, b over 4 plus a over 3. Can you see that? Complete. There's a rule here, bulletproof. It's not going to change. Where's the thing? There's it here. Right? From factorization, first take out an HCF. The number of terms will dictate the approach that we use. Right, I figured out that there's 4 terms, so I'm going to use factoring by grouping. When I did that, I come back here, I have 2, so we're done now. So we did this here, now we come here and distribute. We distribute, we confirm, okay, our answer is in fact the same. The last thing that we always have to do is check. Check if every factor or every bracket, if you want to look at it like that, is infactorable, because that's what we mean by factorized fully, when it's in the simplest form. How do you do that? Go back up and follow the same factorization steps for each bracket. When we did that, we did it for this bracket. There's no HCF. Done. There's 2 terms, but those 2 terms are not perfect squares or perfect cubes, so that's in the simplest form. When I do it for this here now, I can see that there's no HCF, but there's 2 terms that can be factorized using dots. And so when we do that, we come back, distribute, check. Once you do your last checking step, I can't simplify any of this further. So that's when I know I factorized fully. Yes, so that's what we're doing there. Yeah, you see, a question like this here, right, Rika, we didn't talk about U substitution, but it's in the videos, right? But you would agree, if you looked at this here, you would firstly agree that this is a exponential expression. When we're solving for an exponential expression, right? We're solving for an exponential expression that has plus and minus signs. You're going to follow all that steps there, but see what's the last thing here, factorization. So we have to somehow use factorization here. But first, let's get all of the bases into prime bases. So 25 will become 5 to the power 2x minus 1 over 5 to the power x plus 1. If I re-express this, becomes 5 to the power x raised to the power 2 minus 1 over 5 to the power x plus 1. The most deceptive number in maths is what? 1, because it can be a perfect square and a perfect cube. And you know what? This is why it's so powerful, because here, I know that I'm dealing with an exponential expression. I know that I have to somehow use factorization, isn't it? And so if I'm working in reverse, I reverse engineer this whole thing here now. Check here. I need to use factorization, but if I look at this here, I don't know how, right? But if I come back here, I can see, I have 2 terms. So I have to either make use of dots or sum and difference of cubes. But it's quite evident, we're going to make use of dots. Can you see how we reverse engineer everything once the theory has been established? So it'll be 5 to the power x plus 1, 5 to the power x minus 1. Do the distribution, do the checking and see, but this is in the simplest form, over 5 to the power x plus 1. And then the 5 to the power x plus 1, 5 to the power x plus 1 will cancel. So we're left with 5 to the power x minus 1. If you've been paying attention, this is a fraction. The denominator cannot be equal to 0, but the denominator will never be 0 because we got an asymptote of y is equal to 1, isn't it? A times b to the power x plus q plus 1 plus q, 1. And this function here, because a is greater than 0 and b is greater than 1, the inequality signs point in the same direction, so we have an increasing function above the asymptote. Sorry, which is there. So there's no, what's this here? This is the same as y. There's no x value that I can input into this function that'll output a y value that will be 0 or less than 0. Right? But we're more worried about, will it ever be 0? No, it won't. Because it can't even touch 1. How is it going to even get to 0? I can't pass 1 because 1 is an asymptote. It will never get to 0. And so that's why you don't have to state any restrictions here. Okay, guys. Right. So yeah, I'm just gonna end this meeting, and then we can have a short, say 10-minute break, and then we'll just go over some functions questions, and then we can close off the session. Okay. So yeah, you can log out, and we'll meet up at exactly 3:30. Okay. Perfect.